Now have a look at page 20 of your worksheet. This would be November 17 P41. So two coils C and D are placed close to one another as shown in this figure here. You have coil C and you have coil D. So notice that coil C has current flowing through it. It's flowing through the coil. And then after that, you also have another coil D here. Coil D has no current flowing through it, but it has a voltmeter attached to it. So here, they tell you that the variation with time t of the current I in coil C is shown in this figure here. On figure 5.4, show the variation with time t of the EMF E induced in the coil D for 0 to T5. So how do you make sense of this question here? Let's imagine that this one is coil C that the question gave you. This is your coil or your solenoid where you had current flowing through it like this. And then near to your coil C, you have coil D where you had something like this. But there's no current flowing through it, but you have a voltmeter attached across it. How is an EMF going to be induced in this case here? There's no relative motion between your conductor and your magnetic field, but rather there's a changing magnetic flux right now that causes your induced EMF. Here, there's no relative motion. There's still going to be induced EMF. It's mainly due to the fact that your conductor is inside a changing magnetic flux or changing magnetic field. So if you look at coil C, current flowing through coil C itself will actually cause a magnetic field. So that magnetic field probably looks something like this. So current through coil C produces a magnetic field. And then after that, since coil D is close to coil C, the magnetic flux from C links to D. You can assume that coil D is very close to coil C. They're not in contact, just that they're very close. So since they're very close, you can imagine that the magnetic flux that was produced by coil C, some of it actually went through to coil D. It was linking to your coil D. There's actually now flux linkage in coil D. And then after that, another thing to note here is that since flux is proportional to current, as current changes, flux changes. Okay, as current changes, flux changes. Then after that, therefore, coil D has rate of change of flux linkage, EMF is induced. So this is the sequence of events that you can actually use to understand this question. Current through coil C gives you a magnetic field. Because coil D is close to coil C, the magnetic flux from C links to D. And then since flux is proportional to current, as your current changes, your flux changes. Coil D will experience a rate of change of flux linkage, EMF will be induced. Okay, now you may be wondering why I say flux is proportional to current. It's due to some equations that you've learned before this. You remember in the magnetic field chapter, I told you that for a solenoid, the magnetic flux density is mu naught Ni. But I told you that this equation is actually not really required to be remembered in your syllabus. If your question requires it, they will give you in the question itself. So we know that the magnetic flux density of a solenoid was B equals to mu naught Ni. If your mu naught and N are constant, that would have meant that flux density is proportional to current. This is the first relation. And then after that, in this chapter itself, you learn that flux is actually the product of flux density times with area. If your area is constant, doesn't this tell you that flux is proportional to B? This is the second equation. So flux density proportional to current, flux proportional to flux density. If you were to combine both of these together, you're going to get flux being proportional to current. So that if you have current changes, you're going to have flux changes too. That's how I got this relation here. So if your current changes in coil C right now, it causes the flux to change. And at the same time, because coil D is linked to the flux from coil C, you have flux linkage change, or rather rate of change of flux linkage, you're definitely going to have an EMF induced. So what the question is trying to ask you to do now is to find out the EMF induced in coil D. That's the reason why you had a voltmeter here in the first place, to measure the EMF induced. So how are you going to get the EMF induced by just looking at the graph of current versus time here? Okay, this one, you can try to think of it as this. Just now I told you that your flux is proportional to current. You could also say that flux linkage is proportional to current. It's the same thing. You're just basically multiplying with a constant at one side only. All right. So flux being proportional to current is actually the same as flux linkage being proportional to current too. Then the second thing to note was that when you're talking about EMF induced for coil with N turns, it's actually rate of change of flux linkage, which is this one. You can just omit the negative sign. In the notes, you notice that there's a negative sign put there, right? The negative sign there was just merely meant to tell you that the EMF induced is opposing the flux change that caused it. It's actually there to indicate to you the presence of Lenz's law. But here we're really just interested in the magnitude, so we don't really need to bother about putting a negative sign here. That's unnecessary. So EMF being rate of change of flux linkage, there's something from there that you can then do. All right. So if you look back at the first point that I wrote here, just like I told you that flux is proportional to current, flux linkage is proportional to current. Because of this relation that you have here, you could say something like this. Variation of current with time is similar to variation of flux linkage with time. Because flux linkage is proportional to current here. If current varying with time has a certain shape, the variation of flux linkage with time will also be similar. Or maybe I write it the other way around. Because flux linkage is proportional to current, variation of flux linkage with time is similar to variation of current with time. Okay, this one makes a bit more sense to you now. So what I mean by that is something like this. If you look at this current versus time graph, the variation of current with time looks like this right now, right? Because flux linkage is proportional to current, the variation of flux linkage with time will follow the variation of current with time. So meaning to say, if I were to try and plot out a graph of flux linkage versus time, it will follow the exact same variation as current here. That's the significance of point number 1. Because I noticed that my current varies like this for current time graph, my flux linkage versus time graph will also vary in a similar manner. I know the shape would look like that. Maybe I should write something else here. The graph shapes are similar. So let's now assume that this is the graph of variation of flux linkage with time. And then this is where point number 2 comes into play. If EMF is defined as rate of change of flux linkage, this is actually going to be the gradient of your flux linkage time graph. So now you conveniently have a flux linkage versus time graph work out here. Your gradient will actually be a measure of your EMF. So here, what you do is that you look at the gradient in order to work out what is the EMF. So of interest to you are certain sections of your graph here. You can see from here that this one is gradient 0. So your EMF will be 0. You can say the same for this part too. This part here is gradient 0. So EMF is also 0. And then this part here is again gradient equals to 0. So EMF equals to 0. And then as for this part here, the slope part here, you could say that the gradient is constant. So your EMF is constant too. But how about this other section in red? How would you describe the gradient? So this part here, you could say that your gradient is constant, is opposite direction. And can I say anything about the magnitude? If you were to relate to this gradient and this gradient in terms of the steepness, in terms of the magnitude, which one seems to be larger? Here you can see that your magnitude is actually larger for this one. The steepness is actually more. So gradient is constant, opposite direction, and then is also steeper in terms of the magnitude. So that means the gradient magnitude is larger. So what does this tell you then about the EMF? Therefore, EMF is constant, opposite direction, and larger magnitude. The gradient being constant will tell you EMF is constant. The gradient being opposite direction will tell you that EMF is in opposite direction. The gradient being steeper will tell you that your EMF is going to be larger magnitude. So you're thinking, how do I know that the gradient here in the red section is actually larger? You can think of it as this. Your gradient is actually usually defined as the change in y value over the change in your x value, right? So you can see from here that if I consider this as the change in my x, the red section actually has the same change in x. So if change in x is constant, that means gradient is directly proportional to the change in y. So now I look at the change in y values for the first gradient. This is the change in y. But then I look at the change in y value for the second gradient, which is this one. This is my change in y for the second gradient, right? You can see clearly that this change in y is larger than this change in y. So therefore, I can say that the gradient is going to be larger for the second section here. So delta y being larger would mean that my gradient is larger. And that is applied for this part here. So when it comes to finding your EMF induced, you will notice that all the time, you're actually just looking at the gradient of the graph that's been given. How you arrive at the gradient part of it, this one, you can actually derive it out, but in your exams, you're actually not required to do so. You are not required to explain it. So If you want to make your life simpler, just know that it's always going to be your gradient or whatever graph is given to you, like what I've done here. If I wanted to draw a graph of EMF induced versus time, like E versus time, the first section is 0 EMF. So I get something like this. This one will be from 0 to T1. 0 to T1. And then the second section is this one. You have the EMF of a certain value is constant. It could be that this one will be something like this. From T1 to T2. And then after that, this section here is having 0 EMF because the gradient is 0. So you get 0 over here. This is from T2 to T3. And then for the last section, which is this one, you have EMF constant, opposite direction, but larger magnitude. It's going to be a straight horizontal line, but it's going to be in opposite direction. So it's going to be at the bottom. And then because it's larger magnitude, it should be longer than the first one here to indicate to you that it has a larger magnitude. This one will be from T3 to T4. So that's why your graph here looks something like this right now. You notice that I started off with positive EMF here before moving on to negative EMF. If you have drawn your graph with negative EMF first, followed by positive EMF like this, it's also fine. If say you had drawn your diagram like this, where you started off with the negative EMF first, followed by a positive EMF, which is the complete opposite of what you have here, this one is also acceptable. This one is okay. This one is also okay. The marking scheme really just wants to see that the EMF induced are in opposite directions. So either one is acceptable. The next question that you can have a look at is page 12. This would be November 2016 P41. So for the first part of your question, state what is meant by Faraday's law of electromagnetic induction. So you could say that the magnitude of the EMF induced is proportional to the rate of change of flux cutting or rate of change of flux linkage. This was more or less the old definition of Faraday's law of electromagnetic induction. But for the more recent ones, they've actually kind of shortened it where you just say that magnitude of induced EMF is directly proportional to rate of change of flux. This one is the more recent ones that I've noticed is inside your marking scheme. As long as you have the wording rate of change of flux, that will be good enough already. This is actually a general case. A more specific case would be rate of change of flux cutting or rate of change of flux linkage. But rate of change of flux works just as fine. Another thing that I should mention to you is that always make sure you mention the word rate. Okay, rate of change. Because this is the keyword here. If you just say it's equals to change of flux cutting, change of flux linkage, that is actually not the correct one. You must say rate of change. Then if you move on to B, part B, let's go through that question first. The diameter of the cross-section of a long solenoid is 3.2 centimeter as shown in this figure. A coil C with 85 turns of wire is wound tightly around the center region of the solenoid. The magnetic flux density B in Tesla at the center of the solenoid is given by this expression, where B is pi times 10 power minus 3 times I, where I is the current in the solenoid in ampere. Show that for current of 2.8 amps in the solenoid, the magnetic flux linkage or coil C is 6 times 10 power 4 Weber. So if you look at this question here, they give you this particular equation for the magnetic flux density B at the center of the solenoid. You had two solenoids here actually. this long solenoid here, and then another one that they call coil C here. So the magnetic flux density at the center of the solenoid is given by this equation. So they want you to find out what is the flux linkage in coil C. So the keyword here is the flux linkage. That's what they want. Flux linkage is N phi or NBA. Yeah, how do you get NB here in the first place? This one I actually didn't really mention to you just now. Because you know phi is BA. If you say flux linkage is equals to N phi, you're really just substituting for phi here. So eventually you get NBA. That's how you got the other form of your flux linkage here. Now you want to find flux linkage in coil C. You know for a fact that you could probably use N phi. If you expand out, you get NBA. So this is for flux linkage in coil C. The number of coil turns must be for coil C. The flux density must be the flux density through coil C. And the area here is supposed to relate to the area of coil C. Okay, all the variables here must relate to coil C. So here, in this part of the question, they told you that the magnetic flux density of the solenoid, center of the solenoid is already given by this equation. Your B, you can further expand it and replace with this. So right now, if you use what you know from the question, coil C had 85 turns, B is pi times 10 power minus 3 times I. Your I here is actually the I in the solenoid. Just be careful about that. And then right now, the area for coil C, notice that there's 2 pi here. Why is there 2 pi here? It's because you're talking about the area of coil C. Area is actually pi over 4 d squared. That is actually what you have over here. Okay. What I did here was actually something like this. Pi r squared pi d over 2 square. This one is what you're seeing right over here. I'm taking pi multiplied with the diameter divided by 2 and squared. Your diameter is 3.2 centimeter. Remember to change it down to meter. And then finally, don't forget to square it. Eventually, you'll get the answer as 6.01 times 10 power minus 4 Weber. You round it up to 2 SF, you'll get 6 times 10 power minus 4 Weber. All right. When your current is flowing through your solenoid, the current flowing through the solenoid will produce its own magnetic field. You will have its own magnetic flux that probably looks like this. So this B that you have here was pi times 10 power minus 3 times with I. So because your coil C is wrapped directly around your solenoid, whatever magnetic flux density that you have produced by your solenoid will also be the same magnetic flux density in coil C, because coil C was wrapped directly around your solenoid here. So that's why here, just now I told you that your B here, for your coil C, you use this, but then here, your current is the current in the solenoid itself. Because this one gives you the magnetic flux density around your solenoid, but at the same time, it's also the magnetic flux density in your coil C. Okay, then after you move on to the next part of your question. They tell you now that the current I in the solenoid is reversed in 0.3 seconds. Calculate the mean EMF induced in coil C. So here, how do I find out the EMF induced? So as I mentioned to you just now, as current flows through your solenoid here, you will get a magnetic field produced that probably looks like this. It's the same magnetic field that passes through coil C, The magnitude is given by this. And when it comes to your magnetic field, there's supposed to be some direction associated with the magnetic field. Let's assume that for current direction like this, you're going to get a magnetic field that's pointing towards the right side here. This one is if your current direction is something like this here. What if you were to reverse your current, like what the question mentioned? They told you that your current is reversed in the opposite direction. So this time, your current, rather than flowing like what is indicated inside a blue arrow, your current is now flowing like this. So the same current flows through your solenoid. It's going to produce a magnetic field, but the direction of that magnetic field would be in the opposite direction now because your current direction is in the opposite direction. So rather than have it pointing towards the right, it's going to point towards the left. All right. And again, this same magnetic field is passing through your coil C. So you can imagine that whatever magnetic field that you have here is also the same magnetic field in coil C. So what the question wants you to do right now is to find out what is the EMF induced in coil C. All right. So there is going to be a change in flux linkage for coil C here, because originally the flux linkage through coil C was pointing towards the right, but now the flux linkage is pointing towards the left. There is actually a change in flux linkage here. So therefore, you're going to have an EMF induced. But how do you calculate out the magnitude of the EMF induced? It'll probably be a better idea just to draw some graph out just to see how things look like. Now, they told you that your current was reversed in a time of 0.3 seconds. You can think of it as being similar to something like this. Your current was originally 2.8 amps. This is a graph of current versus time. They suddenly reverse it in the opposite direction so that it becomes negative 2.8 amps. And they did it in a time of 0.30 seconds. Now, if I wanted to relate this with flux or flux linkage, what I could say is something like this. Just now, based on the derivation that I told you, I mentioned to you that flux is proportional to current, flux linkage is also proportional to current, because I said that B is mu naught and I. If mu naught and N are constant, B is proportional to I. This is relation number one. And then after that, you also know that flux is BA if your area is constant. Flux is proportional to B. This is number two. So that if you were then to combine both of them together, 1 and 2 together, 1 related to 2, you get flux is proportional to current. That's how you got this. And then you can actually expand it to include flux linkage. So I mentioned to you then, based on this relation, that variation of flux linkage with time follows variation of current with time. In other words, they have the same graph shape, isn't it? So if right now my graph of current versus time looks like this, if I'm trying to convert it to a graph of flux linkage versus time, I'm actually going to end up with the same thing. It probably looks like this right now, following the exact same shape, where you have this, 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 and this. Now, if you wanted to then find out what is the value of your flux linkage right now, you actually can make use of what you found in part A, the first part of your question right over here. You already proved that the flux linkage in coil C is 6 times 10 power minus 4 Weber. So here you could say that you have 6 times 10 power minus 4 Weber. If your current direction was reversed, your flux linkage will also reverse. You are going to have the same magnitude, just that it's in opposite direction. So this is the flux linkage right now over a time of 0.3 seconds. So when you are asked to find out what is your rate of change of flux linkage to get EMF, you need to first find out what is your change in flux linkage, right? This is your change in your flux linkage. It's actually 2 times of 6 times 10 power minus 4. So now, if you wanted to proceed to find out what is your EMF, you know the flux linkage change. You also know what is your time. You can now find out your EMF. Because EMF is really a change of flux linkage. It's change in flux linkage divided by your time. You know the value is twice that of 6 times 10 power minus 4. Your time is 0.3. So you solve this equation, you eventually be able to get your EMF induced as 4 times 10 power minus 3 volts. Change to milli by dividing by 10 power minus 3, you will get 4 millivolts. So this is how you understand this question. Now, in general, every time you read your question that asks you to find out something about your EMF induced and they tell you something is reversed, like in your case, current is reversed, more often than not, you will always notice that your working involves you multiplying with 2. As we go along with the examples, you will notice that. So right now, for this question, you already found out that the EMF induced is 4 millivolts. And then after that, if you move on to the second part D here, they mentioned to you that the current I in the solenoid B is now varied with time as shown in this figure here. This is the graph of current versus time. Use the answer in C, the one that you just found, to show on this figure below the variation with time t of the EMF E induced inside coil C. So this is the current in the solenoid. So from this graph of current inside the solenoid versus time, you're supposed to produce a graph of EMF induced in the coil C versus time. So this one, similar to what I've explained to you, the first thing you should always realize is that your flux linkage is proportional to current. This was the derivation, but the derivation here is not something you need to do all the time. You don't even need to show this. They won't even test you on this. So if flux linkage is proportional to current, this is the only relation that I need you to know. If your flux linkage is proportional to current, this in turn means variation of flux linkage with time follows variation of current with time, which means they have same graph shape. This one coincidentally is the graph of current versus time. If you want to then work out a graph of flux linkage versus time, it's going to be this same shape too. So from here, what you then can do is that you want to find the gradient of this graph to work out your EMF. Because you know that EMF is equals to rate of change of flux linkage, which is going to be equals to the gradient of your flux linkage time graph. So you need to look at the gradient. So if in your exam you are short in time, you actually don't need to do all of this. You just remember it's always the gradient. So like here, there are a few sections that are of interest to me. This section, and this section, you can really say that gradient 0, EMF 0 for these sections here in green. Then how about this section here? Now, notice that there is something about this section here that kind of matches what the question had described to you. if you look at your previous question, they ask you to find the EMF induced in coil C if the current is reversed in a time of 0.3 seconds. Your current was 2.8 amps. You reverse the direction in 0.3 seconds, which in turn got you this EMF value of 4 millivolts. This pink color section that I highlighted to you here is actually that situation described. You can see that this is 2.8, and then this one is negative 2.8, and it's occurring over a time of 0.3 seconds. So you already know from here then that your EMF is going to be 4 millivolts. The value is something that you would have already found. The hint that you can actually see from your question is that they told you to use your answer to C to show on the figure below the variation of EMF with time. So they actually wanted you to look at C. You have to relate what you just found in C to this graph, which is the pink color section here. So here, what I can say is gradient is constant. My EMF is going to be constant at 4 millivolts. So that part is the pink color part. Then how about the other part here in blue? You could say that your gradient is constant, is opposite direction, but can I say anything about the magnitude? Is it steeper or less steep? It's actually less steep, but by how much? Since I'm really being given values here for my first EMF, you would be required to find out the value of the second EMF too. So how do I know what's the value of the second EMF? By looking at how much different is this gradient compared to the first gradient. So remember just now I told you that your gradient in general is found by finding the change in y value over the change in x value. So let's consider these two gradients that you have here. You're actually having the same change in y. You see they're both stretching by the same amount when it comes to the y values. So here I can actually say that delta y being constant would mean that my gradient is actually inversely proportional to my changes in x. So let's consider what are my changes in x then. This was my change in x at 0.3 seconds. This is my change in x at 0.6 seconds. The change in x is actually twice right now. So if my change in x is 2 times as much, my gradient will actually be 2 times as less. It's actually half the value. So like in my case, this gradient here is constant, is opposite direction, is actually half as steep. Okay, this one, the gradient is half as steep, or rather, you can also say half the magnitude if you wanted to. So how does this translate to your EMF value then? You can then now say this when it comes to your EMF value. Your EMF is going to be constant, opposite direction, and half the magnitude. Therefore, your EMF is negative 2 millivolts. So now, if you then want to plot out your graph, this is what you expect to see. The green sections were basically where you had 0 EMF because gradient is 0. The pink section is where you had EMF of 4 millivolts. So you have to indicate it right over here. And then the blue section was actually the part where you had half the EMF but in opposite direction. So you'll be negative 2 MV here. Your graph given here, there are values for the x-axis, but there are no values for the y-axis. So you are supposed to mark out your own values on the y-axis here. A good value to use would be 2 for every 5 boxes. Then you'll be able to mark out your graphs nicely. So once you draw the horizontal lines, just make sure you draw some other lines to join the lines together. Don't leave it hanging or floating there. So this is the actual graph shape that you should get. And same thing like what I mentioned before, if you were to draw it in an opposite manner like this, this is also acceptable. The marking scheme really only just wants to see the EMF being in opposite direction. It doesn't matter how you start it off. So this is one graph plotting question. Okay, so if you're okay with this, then let's move on to page 4. This is March 16 P42. It's a slightly different question, okay, but you notice there are similarities in how you answer them. So here you have a small core of wire situated in a non-uniform magnetic field as shown in figure 10.1. The core consists of 40 turns of wire and moves with constant speed in a straight line. The core has a displacement of x from a fixed point P. The variation with x of the magnetic flux in the core is shown in this figure here. So the core is moved at constant speed between point P and the point where x is equals to 3 centimeter. Calculate the change in the magnetic flux linkage of the core. So you again want to look at the change in flux linkage. They're not asking you about the change in flux, they're asking you about the change in flux linkage. So if anything, this is the term that you need to be careful about in your question. Are they talking about flux change or flux linkage change? So if you read the question, they want the flux linkage change between point P and x equals to 3 centimeter. So x equals to 3 centimeter is right over here. Point P is going to be here. This is where point P actually was, because they told you that your displacement x is measured from point P. You can see from the diagram itself here that if this is point P, x is measured from point P. So where x is 0, that is where point P is. So you're actually going to consider from here all the way to here only to find your magnetic flux linkage change. So this graph that you have here is already a graph of flux versus distance. It's not flux versus time, it's flux versus distance. You want to find the flux linkage change between these two ranges, between these 2 points. So if you were to get the difference between this point and this point, this is really just change in flux. You want to get flux linkage change, you need to multiply with n. Because you can say that if flux linkage is this, change in flux linkage is going to be this. So change in flux linkage, you just take the number of core turns, multiply with your flux change. 5 minus 3 times 10 power minus 6, you're going to get 8 times 10 power minus 5 Weber. So this one will be okay for 1 mark. Then you move on to part 2 of your question. The EMF induced in the core is 5 times 10 power minus 4 volts. Find out the speed of the core. Here, they don't want you to find the EMF induced. They gave it to you already. Instead, they want you to find how fast was your core moving. So to do this question here, let's consider this. If EMF is defined as rate of change of flux linkage, you already know the EMF value. You already know the flux linkage change. What you could find out of it was actually the time taken for your EMF to be produced. It's actually just going to be 0.16 seconds. So if you want to find out what is your speed, there is a relation between speed and time where you say that speed is equals to distance over time. The speed is what you want to know. The time is what you already found out. So what about the distance? The distance is already something that you could also find out already. Because you see, this one being part 2 is actually related to what they wrote in A here. The coil is moved at constant speed between point P and the point where X is 3 centimeter. Then you have part 1 here, and then you have the part 2 that you're looking at. So for the part 2 that you're looking at, it was really your coil moving between point P to X equals to 3 centimeter. Your distance is actually 3 centimeter. This was your distance move. So since you know the distance, since you know the time now, you can now work out what is your speed. So the next part of your working would be this one here, where you say that speed is the change in distance over your time. Distance is 3 centimeter, change to meter, time is 0.16, eventually your speed will be 0.188 meter per second. So that one is pretty straightforward here. Okay, then we move on to part B. On figure 10.3 below, sketch the variation with X of the EMF E induced in the coil for values of X from 0 to 6 centimeter. They now want you to find out the EMF induced from 0 to 6 centimeter. Now, same like what I mentioned to you for the past 2 questions, almost always you are always going to look at the gradient in order to work out your EMF induced. But what this question differs compared to the previous 2 was that this one is not flux versus time, but it's flux versus distance. The ones that you used before this was flux linkage versus time. Specifically, the x-axis was time. But now this one is x-axis is your distance. You can still eventually work out that the gradient is going to be your EMF induced. So I'm just going to explain to you the logic behind it, but just know that you are not required to show this inside your exam. So think about it. The first thing that you know was speed equals to distance over time, x over t. They say that the speed is constant, so v is constant, that means x is proportional to time. This is number 1. Then number 2, EMF being rate of change of flux linkage. If you just bring out your number of coil turns, this one will be n times rate of change of flux. N being constant here would mean that EMF is proportional to the rate of change of flux, which in turn will tell you that EMF is proportional to the gradient of your flux time graph. So right now, there is one relation that you can then say, because x is proportional to t over here, a graph of flux versus time would follow the same shape as a flux versus distance graph. So here, what this means is that you had a graph of flux versus distance that looks like this. But because you know that x is proportional to t, you could also then say that flux versus time will follow the same shape. So here, you can say that in this existing graph, if this is flux versus distance, a graph of flux versus time will also be having the same shape right over here. So from this part here, you will then know that you are really just going to get the gradient only, because a graph of flux versus distance is the same as flux versus time. So you just get the gradient. That one will give you your EMF value. So now if you just look at this part here, gradient is constant, EMF is constant. By right, your EMF will be 5 times 10 power minus 4 volts. This is what the question already told you in part 2. They already told you that here. Okay, so this one is 5 times 10 power minus 4 volts for the EMF induced. How about the second part here? Okay, now for the second part here, you can say the gradient is constant, it's opposite in direction. You can eventually work out that it's going to be twice the magnitude, because you again have to look at the changes in y and changes in x. This one is your change in x. Both of them are the same, but this one is your change in y. So gradient being equals to change in y over change in x being constant would mean that gradient is proportional to change in y. So your change in y is 2 times as much. Your gradient will be 2 times as much too. So here, gradient constant, opposite direction, twice the magnitude. Your EMF is going to be negative 10 times 10 power minus 4 volts. Then you wanted to draw out your graphs, it will just be something like this. It's just going to be this straight horizontal line until 3 seconds, followed by another larger magnitude EMF in the opposite direction from 3 to 6 centimeter. Now, because this question is only worth 2 marks, there was actually no need for you to mark out any values. The question that you just did previously, the x-axis values are marked out, and then after that, you had to purposely mark out your y-axis value and indicate out the correct EMF values. For this particular question, there is actually no need to do that because it's only worth 2 marks. All right. So right now, since it's only worth 2 marks, even if you had purposely marked out the value of 5 times 10 power minus 4 volts here and negative 10 times 10 power minus 4 volts here, it won't be credited because the marks isn't allocated. Okay, but if you wanted to show, it's possible. All right. So sometimes you have to use your best judgment to see. If necessary, you see that the marks here is too little, probably you are not required to show the values. But you see that the marks is maybe 3 or 4, like the previous question, then definitely you have to show. Next one should be page 27. Let's have a look at page 27. This is March 18 P42. For the first part, define what is meant by magnetic flux. Magnetic flux, you know, is phi equals to PA. So you say it's the product of magnetic flux density and area perpendicular to the flux. So you always need to make sure that you mention this. The flux must be perpendicular to the area. And then after that, state Faraday's law of electromagnetic induction. Magnitude of induced EMF is directly proportional to rate of change of flux cutting, or rate of change of flux linkage, or rate of change of flux now. So no issues here. Then you move on to part B. So for part B, a solenoid has coil C of wire wound tightly about its center as shown in this figure. Coil C is 96 turns. The uniform magnetic flux phi in Weber of the solenoid is given by this expression, where I is the current in amperes inside the solenoid. So again, you had something similar to something you just done. You have a solenoid here, and then wrap around your solenoid halfway is another coil, another solenoid. So in the next part here, they ask you to calculate the average EMF induced in coil C when the current of 3.5 amps is reversed in the solenoid in a time of 2.4 milliseconds. So remember just now I told you, whenever you see something inside a question that tells you that something is reversed, like in your case current, more often than not, you will need to multiply something with 2 inside your working. So right now, if you look at your question here, for your case, right now you have the solenoid like this. If you imagine that current is flowing like this, it's going to produce a magnetic field or magnetic flux that probably looks something like this. So this is the magnetic flux that is produced by your solenoid, which also happens to be the same magnetic flux that passes through your coil C. So in your case, this is the current direction. Maybe your magnetic field or your magnetic flux is going to have a direction in this direction here. The question then mentioned to you that your current is reversed, right? If you look at the other part of your question, they told you that your current is reversed in a time of 2.4 milliseconds. So you can imagine that now if your current is reversed, rather than having flowing in the red colored arrow like that, it's flowing according to the orange colored arrow that you see here. So you're still going to produce a magnetic flux inside your solenoid and subsequently called C, but this time the direction will be opposite. So in your case now, the important thing that you remember was that flux is proportional to current, flux linkage is proportional to current. So if you try to look at the graph of current versus time now, you probably have something that looks like this. Your current is reversed in a time of 2.4 milliseconds. But the current magnitude I believe was given to you, this one is 3.5 amps. This one will go on to negative 3.5 amps. So right now, if you have wanted to find out the EMF induced, you can consider that its rate of change of flux linkage. So your flux is already given as this one, 6.8 times 10 power minus 6 I. In your case, when it comes to the change in your flux linkage, the N remain constant, but the flux was the one that changed because your current changed. This one is flux at a particular current value. So you have change in flux is going to be 6.8 times 10 power minus 6 times your change in current. So this one, if I wanted to rewrite it, it will just be N times with change in flux over delta T. Okay, now maybe I don't make things confusing. I'm just going to write it as N times 6.8 times 10 power minus 6 times with delta I divided by delta T. So I need to find out what is my delta I here, my change in current. My change in current is actually going to be this one, which you can see is 2 times of 3.5. So now if you were to put the values in, your cost here is 96 turns, your 6.8 times 10 power minus 6, your current is 2 times 3.5, your time taken is 2.4 milliseconds, change out for milliseconds. Eventually, you will get the answer as 1.9 volts. So that's the answer that you have right over here. Notice that at some point, you definitely need to multiply with 2. What you need to multiply with 2 with sometimes vary. In the last question that you did, you multiply the flux linkage by 2, if I'm not mistaken. In your current case, you multiply the current by 2. So what you multiply with 2 sometimes vary according to the question. Right, C, you can't really do it yet. This one is actually related to AC circuits. Once we go through AC circuits, I'll probably make a passing comment on that. Okay,